Mr. Bari from Columbia University.
And my name is Suborno Bari, who's doing my bachelor in math with a minor in physics at NYU.
Today we're going to do a very important 2D kinematics, and that is the trajectory of a kickball. So Suborno, what I have over here is position versus time. Can you construct a diagram for a kickball?
All right, so I'm going to say
from 0 to 0.
Is this position in the Y?
dy, yes.
Okay, so it probably looks something like this.
So let me give you some information. Let's say you kick the soccer ball with initial velocity 20 meter per second at 37 degree, right? So can you please tell us that Vix and Viy, if I want to replace Vi instead of X, I want to write Vi instead of X, what should I replace X by? Cosine theta or sine theta?
Well, cosine theta.
Okay, good. Sine theta. Now this would be 20 cosine what?
Well, this is 20 cosine 37.
And this would be 20 sine
37.
This would be 16 and this would be 12. Now can you
don't think of it this way. Don't think of it as just replacing and stuff. Because if you actually draw the triangle, you'll see this is Vi, this is Vix, and this is Viy. Cosine theta is just the ratio between Vix and Vi, and sine theta is just the ratio between Viy and Vi. Hence why, to get Vix, we just multiply Vi by cosine theta, and vice versa.
That's correct. We're going to get to that in a second. But before moving to that direction, can you tell us whether we should be able to use the Pythagorean theorem to get that thing back?
Yes, indeed.
Why is that? Is this because this one and this one both have the same SI unit, which is meter per second?
Well, yeah, but also that's just how it works. If you put this back, in here, you get Vix squared plus Viy squared, which is equal to the square root of Vi squared cosine theta squared plus Vi squared sine theta squared, which is equal to the square root of Vi squared times sine squared theta plus cosine squared theta. You should know that this right here is equal to 1, which means this is just the square root of Vi squared, which is, well, you know.
And you also can prove it that Vix squared is 16 squared and Viy squared is 12 squared. If you square root them, you get this one back.
Yeah.
Okay. So now we want to create a table that has many things, and that includes location 1, location, initial velocity, time, dx, dy, I.
All right.
Without blocking it.
Well, Vi never changes. It's just the initial velocity.
That's right.
It's just one quantity.
Don't write as a unit, please. It's get too crowded.
Understood.
What else you can do without doing any math?
Well, we can also do.
That's right. We're going to use -10, by the way.
The gravitational constant, which for some reason is listed up here too, even though it virtually never changes. I mean, this little height difference isn't enough.
Someone wrote +10, and I said if it was +10, then you should be going to heaven, because then heaven would be pulling you up rather than ground pulling you down.
Yeah, that's right.
Now, before we do anything, remember we found this one. Vi is Vix and Viy, and Vix is 16 and Viy is 12. So based on this information, which two columns you should be able to, at least which column we should be able to do?
Well, Vx never changes since there's no force in the horizontal direction, meaning there's no acceleration, which means we can just write down Vx or V initial x 5 times and call it a day.
Can we give a reasoning that acceleration due to gravity at the x direction is 0? That's why it remains constant.
Well, there is no force in the x direction. There is only a force in the y direction, which causes this to change. But we can still fill this out as 12. The peak.
Oh, hold on. Before we do this one, this is a function of time. Yes. So let's first find the time.
No, but wait. We don't need that because.
No, I'm trying to teach my student so that we want to follow some kind of order, if that okay.
Okay.
So now, I often tell my student to find the time. You can find the time different way. D is equal to VIT plus half AT square, and VF is equal to VI plus AT. And my student always forget what this come from. So I'm just gonna write it again. VI what? VI cosine
theta
and VI
sine theta.
And this is 20 cosine
theta and 20 sine
20
theta.
cosine 37, and this is 20 sine 37. This is 16 and this is 12. I often tell them this help getting the time, and this one always help getting the range.
Okay, but first let's figure out what the total time is. So
now my student often forget which component of the velocity they should use to get the time. Can you explain them too?
Well,
oh, I should give you the mic actually, because I think that's better. Can you explain them which component they should use over here?
Well, there's no memorization needed, right? Let's say you just throw up a ball 12 meters per second into the air. It's going to follow this trajectory and come back down to the ground. And then let's say you throw it at 12 meters per second into the air and 16 meters per second horizontally. Sure, it will undergo a different trajectory, but is the time any different? Is adding this component making the ball stay in the air any longer? No, the only thing that can keep the ball in the air for longer is increasing the y velocity. The x velocity has nothing to do with keeping the ball in the air, which means that the y component is the one you should plug in.
So the summary is, if the y component is bigger, then the time takes longer. If the y component is smaller, then time takes shorter. Is that right?
Yes.
Okay. So now, can you come over here? Can you tell me, in order to get the time at location 5, right? What I have to replace this d by?
0.
All right. Go put 0. I'm going to ask you the same question. In order to get the time at location 5, what I have to replace this one by?
-12.
Good. One more thing. In order to get the time at location 3, what I should replace this one by?
0.
Good. All right. So let's go ahead.
All right. So 0 is equal to VI, which is 12, t plus half a, which is minus 5t squared. So we get 0 is equal to t times 12 minus 5t, which means there were two solutions, either t equals 0, which, I mean, I guess it works, but that's not the solution we're looking for. We're looking for one where it hits the ground again, which is when 12 minus 5t equals 0. So that means 5t is equal to 12, and t is equal to 12 over 5, or 24 over 10, which is 2.4 seconds, which means halfway through, we've got 1.2 seconds, and these are just midpoints, so we put 0.6 seconds and 1.8 seconds. So now we can just write this down over here.
Just to confirm that we get 2.4 here and 1.2 here.
Okay, well, we get VI, which is 12, plus A, which is minus 10, times T, which is 2.4. So minus 12 is equal to 12 minus 24, which works out.
Okay. Now I wanted to show the T. I wanted to find the T.
Okay, you can do that as well. So you get minus 24 is equal to minus 10t, or in other words, t is equal to 24 over 10, which is 2.4 seconds again.
So that's check. If you use the information at location 5, you get the information at location 5. On the other hand, If you use the information at location 3, you get the information at location 3.
So VI is once again 0, minus 5t.
Minus
So,
10t.
oh, sorry, minus 10t. So you get 10t is equal to 12, and t is thus equal to 12 over 10, which is equal to 1.2 seconds, which corresponds with being exactly halfway.
Excellent. So now we're going to find the Vy, because since Vy is a function of time, earlier Isaac wanted to find the Vy.
Well, yeah, and you'll notice that in the equation Vf equals Vi plus At, or just V equals Vi plus At in general, that it's a linear function. This is the y-offset, or the y-intercept, and this is the slope. Since the slope is negative 10, that means it's going to be going downwards at a very fast rate, kind of like this. This is V in the y direction.
So Isaac, can you show my student how you can find the Vy at location, let's say 1?
Well, I mean, it doesn't really matter. All you have to do is plug it into 12 minus 10t. So for V1, that just for location 1, that becomes 12.
And
for
can
location,
you show location 2 by putting 0.6?
Okay, it's not that complicated. So that gives us 6. At location 3, it's 0, as we know. At location 4, it's minus 6. And at location 5, it's minus 12.
What parabola has, you can divide it in 50-50, right?
Mm-hmm.
So if you cut it in half, the velocity vector, can you tell me what is all 3 location? What is the name of this vector?
This is velocity in the x direction.
And what is the name of this vector? I'm sorry.
That's velocity in the y direction.
Okay, and now can you draw, this is Vy, of course. Can you draw Vxy? Well, at all 5 locations. Is there any Vxy over here, or the same thing?
They're the same thing.
They're the same thing. Okay, now, my student trying to understand why velocity decreases over here from location 1 to 3. Can you explain that?
Well, I mean, it's pretty simple. It's going up at first, but acceleration is pulling it down towards the ground.
Okay, so acceleration, so these two vectors are opposite to each other.
Yeah.
So it's slowing down this way.
Yeah.
Why this one is speeding up from location 3 to 5?
Because at that point, it's starting to travel downward.
Okay.
And gravity is pulling it downward as well, which means that overall, it's going to start speeding up in that direction.
It's because acceleration vector and velocity vector are the same direction.
Yeah, it's like trying to make a U-turn. You're already pushing the brake over here, so it doesn't make sense to say, well, why am I slowing down here and then speeding up once I start going the other way?
Now, the next thing is to understand the Vxy and Vxy. Should we be able to use the Pythagorean theorem?
Doing the Pythagorean theorem, 16 squared plus 12 squared is equal to rad 256 plus 144, which is equal to the square root of 400, which is equal to 20 meters per second. Okay. And the same exact thing goes for 16 and minus 12, which is also 20. 16 and 0 is pretty simple as well, because it's just 16. So we can write that down. And these two are a bit challenging, but we just write these down like this, which is rad 256 plus 36, which is equal to the square root of 292, which is a little bit greater than 17, which is rad 289. So we'll estimate it at 17.1. So we get 17.1 over here. And
no, we're just going to use 17. I'm sorry.
Okay, sure. 17.
Okay. Good. Excellent. Now, can you do now vector addition head and tail? My student having a hard time to understand how you can use head of one vector, put it on the tail of other vector, and put the resultant. So hold on. Can you first start with Vx vector?
That's an extremely small diagram. I'm not using that. So we have Vx and Vy. So all we're doing is we're essentially kind of moving this in space over here. Like I'm drawing a dotted outline right over here, right?
Okay.
So
vector.
Yeah. So it's not like we're actually moving it. We're just drawing a copy of it over here. So then we draw a point at the tail of this end and at the head of this end and connect them.
And what do you call it? Resultant?
Yeah.
Okay. So once you have a resultant, you don't probably need this one since you have the copy of this one on the other side. How you can use SOHCAHTOA to find the angle, and what angle are you trying to find? Is this angle, or this angle?
Well, clearly we're trying to find the angle with respect to the x-axis. So it's going to have to be this angle, which starts out as 37 degrees. So we'll just notate it as that, and
But
ends out in the opposite direction, which is minus 37. And in the middle, of course, it's going to have to be 0 since it's traveling completely horizontally. But then, for these other two, how do we calculate it given Vx and Vy? Well, let's denote it as theta. We know that tan of theta is equal to opposite, which is Vy, over adjacent, which is Vx, which means that theta is equal to arctan of Vy Vx.
At what location you are doing? Location 2. So Vy must be 6 and Vx must be 16.
Yes, so that gives us arctan of 6 over 16, which
That's
I believe
21.
is approximately 20 in this direction and negative 20 in this direction.
So this is how I told my student to understand how they can measure the angle. So I said that this is x and this is y. Being the resultant vector, move it at the origin, go to the x-axis, measure counterclockwise. And whatever angle this one is the angle. For example, angle could be 37. And negative 37,
Negative
this
37.
one would be look like this. So either you have to use negative 37 or 37 clockwise.
Or you can use 360 minus 37 is equal to 323.
That's right. They all are the same thing. All right. Now we finish with this. Now we're going to do dx, dy, and we are almost done.
So the dx is going to just be a straight line since vx is constant. So d is equal to vt if there's no acceleration, which there clearly isn't. So v is always 16, so it's just 16t. 16 times 0 is 0. 16 times 0.6 is 9.6. 16 times 1.2 is 19.2. 16 times 1.8 is 28.8. And 16 times 2.4 is 38.8. dy is a little bit different since there's acceleration. We have to use d equals vit plus half at squared. So that becomes vi is 12, half a is negative 5 since a is negative 10. So then we just plug in, putting in 0 gives us 0 here. Putting in 0.6 gives us, and yes, I know what it is. I'm just actually demonstrating it. So this is 7.2 minus 5 times 0.36. This is equal to 1.8, so we get 5.4. And that means it's also the same this way, and also the same this way.
And in the middle?
In the middle, we get, plugging in 1.2, 12 times 1.2 minus 5 times 1.2 squared, which is, of course, 14.4 minus 5 times 1.44, which is equal to 14.4 minus 7.2, which is 7.2 meters per second.
Isaac, I have a question. Why the max height, okay, the magnitude of max height is equal to the trajectory from 1 to 3?
What?
Max height is 7.2.
Yeah.
And from here to here is also 7.2.
In reality, all we're watching out for is the vertical displacement, which increases and increases until it hits this. The reason these two have the same in reality is because this is just drawing a point from the projection on the ground to the actual max height. This is drawing the trajectory between where you threw it and the max height. There's no difference because both of these points are on the ground. So the vertical difference is the same.
Good. All right. Now my next question is, can we use Pythagorean theorem to get the dxy using dx and dy?
Well, that's the literal definition. So you just get 0 over here since it's 0 squared plus 0 squared. 38.4 here, and then the other three are a bit more tricky to calculate. So we're going to pull out the calculator, and we're going to plug in everything. So we start with 5.4 squared. Now to figure out the angle between the displacement vector and the ground, which is essentially what would happen if you took a look at the ball and then drew a line between the ball and where you were currently standing, found the angle between that and the ground. It's not very significant, but so over here it has to be 0.
But Isaac, the calculator is supposed to give you the undefined if you write 0/0. How can you resolve that issue?
Well, yeah, because it's incredibly small. Because, I mean, there's zero difference between you and the rock. But imagine what happens after 0.01 seconds of you throwing the rock, right?
Okay.
It's barely lifted off the ground at all.
That's right.
So
people can try that, right?
No. Actually, I think there might be a mistake. You know why?
Why?
Because 1 is not actually 0. Think about it. Think about it for a second with me. When you fly off the ground, so this is where you initially threw it, the velocity has basically no change, right? So it just travels 16 whatever t in this direction and 12 whatever t in this direction, approximately. So then the
12 whatever t. No, I thought this is 12t plus minus 5t squared.
No, the time is so small. It's like 0.001 that when you square it, it becomes insignificant.
5t squared, and if you point 0.00001,
this becomes insignificant because, I mean, it just got off the ground.
Okay, speaking of calculus?
Yeah.
Okay.
So then, once you take the arctan, it gives you 12t over 16t, which is just 12 over 16. And what does that give you when you plug it in?
37.
Because that's the initial angle.
Okay. Okay, so Isaac made some assumption. So this one is VIT plus half AT squared, and this is VIT plus half.
How is this half AT squared?
Hold on. And this is at the x direction. So he assumed that acceleration due to gravity at the x direction 0. No, which is true. And he assumes that this one contributes almost nothing because this is 5t squared. Because if you multiply 5 by 0.000000001 squared, this is almost 0.
Once you square a very small number, it becomes even smaller.
So then negative 5 would become negative 0.00001, something like that. Which will contribute nothing to this one. And this is, we know, 12t. So now the proof is excellent.
It is literally the exact same thing as VXY. So I'm just going to copy over all the entries here.
Okay, now we're going to draw some graph and
see what is that going to be? Well, at 0, it's 0. At 0.6, what is it? Well, at 0.6, it's 11. So I'm going to write 11 right over here. At 1.2, it's 20.5.
21.
So it's just under 22, which means it's over here. Or for 1.8, we get 29.3, which means it's almost halfway between 22 and 33. I know that's not fully accurate.
That's fine.
And
at 2.4.
Over here at 2.4, we get that it's around 38.4, which means it drops off even more around here. Now, it might look like a line, but the truth is, it actually gets very wacky around here. We just can't see it because the data points are very far apart. But as it settles, as it keeps on going, this is essentially x times a quadratic term. And this quadratic term gets extremely small as t increases, which means it just settles down into a line.
Very good. So the graph number 1 is similar to this graph, or exactly same.
All right, so this is the exact same as the, Okay, so since that's been removed, well, at uh at 0.6 it's no at 0 it's 20. So I'm gonna draw that over here since it's the topmost value. At 0.6 it's 17, which means it's right over here, which means it goes something like this, like a U shape. And then dyt is just your regular old parabola. It starts at 0, then it goes to 5.4, which I'll write over here. Then it goes to 7.2, which I'll write over here. Then back to 5.4 and 0. So just a regular old parabola. Then Vy is, well, just a line. So it starts at 12 over at 0, goes down to 6, goes down to 0, goes down to -6, goes down to -12. So it kind of gets in Vx's personal space, but Vx is just 16 the whole time. A is just, well, -9.8 or -10 the whole time. And dxt is, well, just going up linearly. So at 0, it's 0. At 2.6, it's 9.6. Well, no, not that close. At 0.6, it's 9.6. At 1.2, it's 19.2. At 1.8, it's 28.8. And at 2.4, it's 38.4. So it's just a line which looks like this.
What would be the equation, or more or less intuition behind the equation?
The equation is just d equals vt, v is 16.
All right, very nice.
Wait, we're not done.
No, can you give me the black marker
Yes.
for 1 second? Most important graph I forgot. dx, dy, dx.
All right, well, okay, sure. So Vx and Vy is pretty simple. So think about graphing all those points. 16 comma 12 goes over here. So let's write this as 16. 16 comma 6 goes over here. 16 comma 0 goes over here. 16 comma -6 goes over here. 16 comma -12 goes over here. It's just a straight line that ranges from 12 to -12 since Vx never changes. Now, dy dx isn't actually that important. It's just a copy of dyt, but it's actually scaled up, kind of. So this is an exact copy of the trajectory. So the thing is, since dx is directly proportional to t, and just t multiplied by 16, this is basically the same exact thing as dy t. But this time, we can actually take a point, draw a vector, and call this the total distance traveled, whereas there we cannot.
Show the dxy here and vxy over there.
Well,
this is called
if we select a specific point, and now this, it would be dy, and this would be dx, distance from the beginning in the horizontal direction, distance from the beginning in the vertical direction. And if we wanted to draw Vx and Vy, we could too, like this. Right, you can. Actually, this doesn't have any meaning here.
Yes.
Because it's the derivative of distance over distance. Here, the derivative of distance over time actually means something. So you could have Vx and Vy.
What did you discover from today's lesson?
Yeah, so we discovered kind of the irregularity of the dt graph, the irregularity of the st graph, how we can express dx, dy, and dxy as vectors on the dy dx graph, and how we can express vx and vy as vectors on the dyt graph, as well as the shapes of some of the other more usual graphs.